So let's continue now with this one. Just a second. Okay. Chapter 51, Structures, Standard Practices. Well, as it is written here, we will make kind of overview of the major structural components on Embraer 190. We're going to talk about SRM, the Structural Repair Manual. We're going to mention this non-destructive testing inspections, NDT, or here it's called NDI. And you know that these two manuals are working together. You remember that structural repair manual is divided again on two parts, like on the aircraft maintenance manual. And in number one, SRM, you can find the components, some general information about the components, but in SRM2, you can find procedures, you can find allowable damage, and there's basic laws and rules concerning the use of the sheet metal, titanium, composite materials. Everything is here. You know already from the introduction chapter that we have a lot of component materials involved in this structure of Embraer 190. Well, we can expect different type of damage on the structure, and as I said, it's very important if you're to be familiar how to use chapter 06, dimension and areas, so much more easily you can identify the specific location when you find a damage. Then it will be really professional from your side to find the allowable damage and to prove that the aircraft can be dispatched or no, following your measurements and following the limits for this exact location. We're going to talk about damage classification. We're going to talk about some repairs, just like in logical sequence. We have some examples, of course, but here my duty will be to make you think in this direction, how we can evaluate problems related with the structure and how to make decision to dispatch the aircraft. As I said, it's very important, this initial assessment, the location, and then the type of the damage. So also to measure the dimensions of the damage is critical for your final decision, go or no go, or maybe repair or whatever. Now we're going to discuss the different options and so on. So here on this schematic, what we can see? We can see structure, yes? Structure of fuselage. So these are, what is this with the red? Come on, tell me. You're professional.
It's called the frame.
Very good. These are the frames. And what is this?
Stringer.
Stringer.
The stringers. Perfect. What is this gray covering here? This gray.
Skin.
This is the skin. Perfect. What is this here visible? Partially visible. Again gray, but it's partially visible.
It's a Q's beam.
No, this here is our belly fairing, which is composite,
the shield.
but later about this. So in this cutout section, also we can see these floor beams. We can see tracks here, and these are, let's say, the most popular components when you talk about the fuselage structure. You know that we also can divide the structure like on primary and secondary, but later about this primary and secondary structure. All this kind of structure is protected. It doesn't matter if it's composite or it is metal structure, it is protected. It is protected because of corrosion, against some kind of contamination if it's possible, and depending of the material which is used for the structure, there are different protections which are used to protect this specific surface, as I said. The most popular is the dinitro. You know, this brown sticky liquid which we are using to protect the structure against corrosion. But before that, the structure is first protected with primer. You know this primer, the green color? Yes. The primer is the first protection for the metal components, and then we put dinitro against corrosion. The primer is protecting against aging, against this chemical corrosion, so-called, but later about this. So we're going to talk about some cleaning up of damage and the different type of inspections. Aircraft structure design ensure stresses are spread through the appropriate structural elements. Okay, so any damage must be investigated, and we always have to keep it like important damage. Okay, because if I want to be more like philosopher here, I will try to give you one example. You are already familiar with air conditioning system, hydraulic, landing gear, yes? And you know that in case of some system problem, some component becomes inoperative, let's say in case of some system failure, we always have a backup. Like for the landing gear extension, as something which is critical for the flight, critical for the safety, we always have backup. We have 3 hydraulic systems. We said lack of one hydraulic system, we will not change so much the control of the aircraft. Also the flight controls. We talk about different problems, jamming, PCU jam, or cables rupture in the aileron system. And every time it was explained, okay, if you totally lost the ailerons, you still have rudder and elevator, yes. If your rudder stuck, the PCU has some jam, the rudder deflected position, we still have aileron and elevator, yes. We always have something like a backup. So pay attention, no backup for the structure, yes. If we have failure of the structure, most of the time, this is catastrophic, yes. So keep in mind that yes, we have sometimes small dents, we have small damages, but you never know if there's something behind this damage. You have to evaluate properly and to properly take your decision. Sometimes we have something which looks like a small damage, it's not a problem, but later this can lead to disaster. So always be responsible, even with the small structural damage, but also carefully and precisely explain all this information that you know about the damage in the book or job card or any official document. I can give you just one example how not to do it, okay? So during removal of air bridge from the aircraft is ready to fly with passengers, everybody on board, they're closing the door, and it was positioned on the terminal with bridge. But the bridge driver, this air bridge driver, instead of removing of the bridge, he started to push the fuselage. He's pushing, pushing, pushing. He cannot stop the process for a while. So finally, there was several dents on the skin and the structure on the frames and stringers. And the guys who were responsible for this aircraft to investigate and to evaluate the damage, they found nothing in the SRM, which is a restriction for dents on the stringer and on the frames. Some damage. Okay, there was no holes. Okay, just dent. So they found nothing in the SRM, and they said, okay, if there is nothing in the SRM, we can release it. So they put in the book, aircraft was hit by the bridge, everything is fine, aircraft released with small dents. Okay, no SRM reference, no dimensions of the dents, no location of the dents, on which frame, on which stringer, nothing. So they released the aircraft without any number. Okay, this is absolutely not professional. Investigate and make your assessment, evaluate the damage, what type, where exactly, on which frame or which stringer, and on the top of that, frames and stringers are very important, you know, structural elements. There is no explanation, sorry, there is no limits in the allowable damage because it's not allowable. It's not allowed to have damage on the primary structural components. But this is an example. If something is missing in the manual or in the allowable damage, or the example is also MEL in the minimum equipment list. If something is missing, it doesn't mean that it is acceptable, okay? If it's missing, we have two options. It's absolutely no-go if it's affecting the flight safety, or if it's not affecting the flight safety, you can just release it, but still, you have to make entry, okay? So be professionals and follow this example, not to do like this, okay? Always make good entries with your assessment, especially when you talk about standard practices and structure. So how we evaluate damage? We have options, different type of inspections. Well, special detailed inspection. This is examination of specific item, installation or assembly to detect damage, failure, or irregularity. What is detailed inspection? Examination of specific area. Once again, make the difference in the words. Special detailed inspection is special for a specific item. Detailed inspection is like a general inspection on some structural area. I will give you examples. Why it's special detailed inspection? Because you are looking for some specific problems, specific damage, specific failure or irregularity for specific component. Just something really specific. And when you have detailed inspection, you have some criteria like damage or failure or irregularity, but you are going to apply these criteria to the entire zone, to the structural area, not to specific item. Okay, so in this structural area, you can expect several components requiring special detailed inspection. So make the difference. They're both interested to detect damage, failure, irregularity, but make the difference between special detailed inspection and just detailed inspection, okay? Also, when we talk about special detailed inspection, we have specifics related with some specialized tools. Maybe we have to use magnifier. Maybe we can use flashlight, okay? Maybe we can use mirror. Yes, maybe it's not direct, you cannot see directly with your eyes. Maybe you need a mirror to check something which is not really visible. All this is special. Special, first of all, because we have some specific component, specific item, and secondary is that we are using some special tools, let's say. Not so special, but we need additional tools like flashlight, mirror, or magnifier. Okay, this is special inspection. Let me go back again with the detailed inspection, this simple detailed inspection. We don't need for this inspection some specific tools. We can use just the normal light in the hangar or outside. Also, you can use mirrors or magnifier or something like this. But once again, the main difference is the zone, specific item or structural area. Okay. So let's go through this logical diagram and we can play together this logic. First, we have damage. Find where the damage component is referred into the SRM. So, is it wing? Is it fuselage? Is it door? Find where it's in the SRM. Identify what kind of a allowable damage is applicable. Find a table with the allowable damage and check if different types of damages are available. Then we have a split here. We have a logic. Is the damage in the permitted area for the applicable allowable damage? This is just to put your attention that if you have permitted damage or no. So, you know, if you have some permitted damage, okay, you will examine the damage, you will find the appropriate inspection, you will make the assessment to look for allowable damage. If in the SRM there's nothing about this area like allowable damage, well, you don't need to look more. You don't need to make assessment because you have to replace the component if there's nothing in the allowable damage list. But let's take this logic here. If the damage is permitted and we have allowable damage, then we're starting our assessment of the damage. We have to check the damage depth, the damage length, and we have to check if there are any additional limitations in this allowable damage task. After we measure the damage, then we have options again. Is it the damage within the limits for permanent rework? If yes, do the rework according to the SRM and everything is fine. If there is no the permanent rework, we have to look for temporary solution or so-called flyby if it is acceptable, because in some cases we have temporary repairs and later we have some limitations. We have a period or some cycles that we can prepare to permanently fix the problem. Maybe with component part replacement, like a piece of skin, for example, or any other component that we can replace, or we can do a permanent rework. It depends. These are our options. If there is a temporary rework for the component, then okay, check if the damage is in the limits for this temporary work. If yes, do the temporary work, fill the book, everything is fine. But If there is no temporary work, we are going to check the typical type of repairs if they are applicable for this area. Okay, these are like the types of the logics here in this case. Example is shown here with the lightning strike damage. Find where the damaged component is referred to the SRM again. Go to the applicable lightning strike damage task. Is it in the area where a flyby for lightning strike damage is allowed? If no, well, we have a problem. We have to look for additional solution. It means we have no allowed damage there. Okay, no, it's not listed in the allowable damage list table, so in the allowable damage table. Then, if it's allowed, this lightning strike damage, we have to do detailed inspection of the affected area. We have to check if there is any damage to the skin. Well, if we have damage to the skin, we have to repair the skin. If no, we have to find the damage length by measuring the distance between the most distant damage spots in the same bay. So later we have to compare this damage with the table with the lightning strike damage task. And then if it's acceptable, okay, we can release the aircraft for 50 flight cycles, for example. If no, we have to check the applicable thickness reduction damage task and to follow the procedure which is in the section. In that case, you're going to need NDT specialists, non-destructive testing, to help you to find what is the thickness of the skin or the structural component in that area. And here is where you can use SRM part 1 to check where you have the different components and their dimensions. Let me go back here to these terms which are related to the structure. We had detailed visual inspection, we have just visual inspection, now we have a general visual inspection. This is a visual examination of interior area, installation or assembly to find obvious damage, failure or irregularity. Here we don't need any specific tools, any specific lighting, no additional equipment. We're just using the available lighting in the hangar or outside if you have daylight. Also, maybe you can use flashlight if it's too dark, but no additional tools. Direct inspection is used for assess a damage. Damage is most circumstances will have to be classified to its extent to determine if it's allowed or requires applicable repair. So have a look what kind of damage we have. Allowable, repairable, or damage which require replacement. Once again, the categories. Allowable damage. Yes, you have damage, you found it, it's okay. Assess the damage, find the dimensions, find the zone, consult with the SRM, and if you can find that your measurements are in the type of the damage, like crack or I don't know, corrosion or dent, depending on the structure, if this type of damage is allowable, and if your measurements are in the allowable damage in the table, everything is fine. I mean, it is fine, like you can release the aircraft, maybe with some simple repair, maybe high-speed tape or something like this. Another option is when you check the table and yes, there is a allowable damage, but the problem is that it's out of the limits. Your measurements are out of the limits. Then you cannot release the aircraft. You have to look for other solution. And the other solution is to repair the damage. You have to check if this type of damage on this specific area could be repaired. If it could be repaired, this is what we call repairable damage, damage that we can repair. And the last option, the last category that you have is, yes, you have a damage. It's not part of the allowable damage list in SRM. It cannot be repaired. So the only chance is to replace the damage chart, the damage part. So once again, allowable damage, repair damage, and damage which cannot be repaired, but we need to replace a part. Also, it's very important for you to identify what type of damage you have. Is it a dent, crease, abrasion, gouge, nick, scratch, crack, corrosion? Okay, so we have different types, and depending of your structure, you can experience different types of damage, and some of them are not present. For example, you know that also the windshields, the windows, they're also structured. They're also structured, but you can find corrosion on the window. Yes, you can find crack. Yes, you can find scratch. So it is very important to identify what type of damage you have, because sometimes they look like the same, and you have to be familiar how properly to identify, is it a scratch or is it a crack? There are differences. Yes, for example, a scratch is a line of damage of any depth in the material and results in a cross-sectional area change, usually produced by sharp object. What about the crack? Crack is a partial fracture or complete break in the material and procedures, the most significant cross-sectional area change. It's usually an irregular line, and it's normally a result of fatigue failure. But I can tell you that in some cases, you can be confused between cracks and scratch. So don't worry if you're not really familiar with all these individual explanations of the different types of damage. Anytime you can find this explanation in SRM. What is crack? What is gouge? What is nick? Okay, so many people are making they mix dent and gouge because they look like similar. Also, very popular for confusions are scratch and crack. Of course, if you are experienced with damage assessment, it will be much more easy for you to identify what type of damage you have. But still, if you have no such a experience, please don't be in a hurry, don't rush, read carefully, examine carefully, and if it's necessary, ask some experienced colleague or use some additional equipment or some additional methods to identify what type of damage you have. Okay, because maybe in your area scratch is permitted but crack is not. Okay, so you have to identify, is it scratch or crack? If it scratch is allowable, then take the measurement, assess the damage. Maybe the scratch will be out of the limits. It doesn't matter that it's allowable, we still have some limits. But if it's crack, it's most probably not acceptable. Okay, I will give you an example because I just mentioned about the windows. Scratch is acceptable on the window, but crack is not. Looking from inside, you are not really sure is it really a crack or scratch. Of course, I have some experience and I can identify. First of all, you know, the scratches you can feel with your fingernail from outside, but the cracks are usually inside the structure, but you never know. When you talk about damage they're not, how to say, every damage is different example, because the location is different, yes, the dimensions are different. So every time when you find a structural damage, it's like a new challenge for us. It's a new challenge because, yes, you know the logic, you know the steps, but actually every damage is individual. Every damage is individual. As I said, because of the location, because of the type of the damage. Even if the location and the types are the same, maybe the size is different. So the size I'm talking about, thickness, the depth and the length of the damage. Because typical for during line maintenance are the dents. Dents are something really typical. So yes, dents, okay, I can assess dents. I'm professional, yes, but there is one story if the dent is on the leading edge. It's another story if the dent is on the inlet cowl of the engine. It's another story if the dent is on the radome. It's another story if the dent is on the door or on the door surroundings. Okay, it's another story if the dent is on the belly fairing on the composite structure. Okay, so we have options all the time. Okay, and be careful with the assessment. Here there is one example given, so I'm trying to go through this example, and we can talk, and we can see the steps, how we evaluate the damage. So during walk around, we see kind of damage here, and we identify it like a dent. Dent is normally a damage area which is depressed with respect to its normal contour. There is no cross-sectional area change in the material. Area boundaries are smooth, and its form is generally the result of contact with a relatively smoothly contoured object. For example, bird, yes, like a bird strike. Have a look. A dent-like form of damage to the skin or panels may be the result of also pinning action of an object containing them. If the inner surface of skin shows no contour change, a local cross-sectional area change should be assumed. Okay, that's why sometimes you cannot identify if you have this cross-sectional change or no. So you have to go inside, and not to go inside, to provide access to check also the other side of the surface. Okay, so allowable damage. We said allowable damage is a damage which can be permitted to exist as it is, or may be corrected with very simple procedure, such as multing out or stop drilling, which are classified as allowable damage. Many times these repairs, with like kind of repair, we do not repair, but anyway, sorry. Repairable damage is applicable to the airplane and can be made by patching or insertion repairs. The use of such methods for general repairs to skin or internal areas is characterized for each structural element in SRM. Once again, as I explained earlier, these repairable damage, they are something that we have to specially check for the special type of damage for the special zone. Okay, so we have a puncture here. The puncture, if it is puncture, this is a damage that does not go fully through a part thickness and does not have a regular shape. It can be caused by hitting on a part with a sharp object. So have a look. Initially, it was looking like a dent, maybe, but maybe later it is a puncture, yes, when you go closer. That's why I told you we have to investigate. Here we have standard practice for oversizing holes and stop drilling, drilling a hole to stop a crack. Here we have some examples, but I'm not going inside with these numbers and these specific procedures. This is like a general practice here. We have to check the distance between the hole and the edge margin, which is at minimum at 2 times the hole diameter. This is when we're doing oversizing existing hole. And remember, when we oversize existing hole, the reason is that during the removal, maybe there were some cracks here, and it's not possible to be like this. We always drill a hole which is a bigger size. And when we drill a hole, it is a bigger hole, it is also possible to have some cracks here. And that's why every hole which is drilled on the aircraft have to be checked with rota test by NDT. Okay, every time when we drill a hole, it is possible to have a minor crack here, which is absolutely not visible with eyes, normal. Even if you're looking with magnifier glasses, it's not visible. You need non-destructive testing, NDT, okay? And I'm not going so much in details because these are specific for the guys which are specialized in the structural repairs. Just keep it simple, just keep in general. If you have hole drilled, you have to do a rota test, because later, if you miss to find the crack, if the hole is not crack free, actually here is the crack, later during the surface of the aircraft, this crack can expand and then to separate piece of the structure or component. Okay, there are also here some examples, some millimeters, some dimensions. Let's don't go in details. The point is that in some cases we can find the crack here. Yes. How we can remove it? We can remove it with another hole, bigger, and to check again. If there are no cracks, everything is fine. But if we still have crack, then we drill another hole. But we cannot continue like this forever, okay? We have some restrictions. So, as I told you, sometimes it's not an easy job to make a decision to fix the problem, okay? Here we have example with scratch. A line of damage we set, which is most probably because of sharp object, and we have this cross-sectional area change. The problem with the scratches is that sometimes they can continue and they can become a crack. Okay. And to prevent this, we're using the blend out procedure. Are you familiar what is blend out? Blending. Blending is when, for example, in this case, we have the scratch, and you know very well that all these scratches, first they are damaging the layer of the paint, then the layer of primer or some protection layers, and then if the scratch is deep enough, it will also damage the structure. We said it's done by a sharp object, and because it's done by a sharp object, usually with your hand, with your fingers, you can feel the sharp edge of this scratch. And because the scratch is very thin, it's very difficult to evaluate how deep is the scratch. That's why we are blending out. Blending out is removal of all these edges. We are making the area smooth. So finally, we can investigate this scratch like a dent. Okay, we are doing this blend out to remove all these sharp edges and to find if there is a crack or it's still like a scratch. And depending of the damage, maybe later you can look on this damage like a scratch. Maybe it will become like a dent, or it will become like a crack. you don't know. But first of all, blend out procedure. Blend out procedure, which is making the area smooth. And here you have to be careful if you're doing this, especially if you're working on the titanium components, because the titanium powder, this dust, titanium dust, which is um, because of the blending out, it's very easy to be ignited. It's material which first of all can cause irritation of the skin, but also can go inside your lungs when you breathe, and also it's very flammable, highly flammable. So be careful. By the way, most of the operators, most of the 145 organizations, they have dedicated guys, dedicated teams, which are really professionals in this repairing of structure. Okay, so in line maintenance environment, for example, me, I had experience with many and different type of damage on different type of aircrafts, 737 and 320 and Embraer 190, and I can tell you that most of the times I can reach a step which I just cannot decide how to proceed, or at least I have no skills to do the blend out procedure. I have no skills to do riveting or something like this. That's why, you know, there is additional, like a specialty in the aviation maintenance, and this specialty, the structure guys. The structure guys, they just study to be to do repairs. Okay, they don't care about the fuel system, they don't care about hydraulic. They are specialized to analyze, to assess, and to do repairs on the structure. Okay, so it's very good, and how to say, it's something really positive if this job is done by professional. Because yes, I was giving you some examples with the different types of damage and so on, but this is your duty. Like a mechanic, like a B1, you should know how to investigate, how to analyze the type of the damage, the zone of the damage. Then the repair itself, or this kind of procedures, must be done by professional. And I can give you one example. It was kind of fresh example. 2 years ago, we had a dent below the first officer, below the captain window here. Most probably because of bird strike. Somewhere here was the damage. So we investigated. It was a kind of not dent but scratch. Sorry, it was kind of scratch, and it was dent with scratch inside. So we stopped the aircraft because we were not sure what exactly we have to do. And then one guy, specialist structure, he came and he said, "Oh, don't worry, I will blend out and everything will be fine." I said, "Okay, do you have experience on Embraer?" He said, "No, no, no. We are structure guys. We are not certified by aircraft type here. We are certified by skills. So I have my experience. I know how to do this. Blend out procedure is a standard practice. It's not a problem." I said, "Okay, be careful because Embraer is kind of difficult and different airplane, and the skin thickness is extremely low." He said, "Don't worry, I'm professional." That was his words. And he started to blend out, and I told him, "Hey, be careful. We are going to make a bigger problem than we have." He said, "Don't worry." He continued to blend out, and later he said, "Okay, just wait a second, I'll come back later." And then he came back with one NDT guy, and they perform measurement of the thickness using the NDT methods, and they found that he blended out too much, and now instead of allowable damage, we have to go to a repairable damage. So we stopped the aircraft for several days, waiting for Embraer to advise for specific repair here, and it took also time for materials to arrive and the repair to be performed. This is just an example how even a professional guy can do something to, how to say, to increase the damage. Okay, so keep that in mind. Okay. Blend out procedure. Blend out is something that it looks very easy and very funny when you do it, but you can cause even bigger damage. Have a look. This is the example here that I was trying to explain with words. Let's say that we have a scratch here, dent and scratch, so we start to blend out. We have to remove material here to make the area smooth and clean of scratch. And later it will look like a big dent. Yes, because we removed, you see, we removed some material. It's not flat anymore. Yes, it's smooth, but it's not flat. So then we have to make the measurements to check the width, to check the radius, to check here, because we are interested also about the fasteners if they're around the damage, and check for damage. This is the blending that we set. In this example, we have this second layer of structure, maybe skin repair. You have to select the proper rivets. You have to use the proper procedure for this riveting, okay? And as I told you, I'm not going in details exactly with this example. There is nothing to remember here like numbers. Just remember the logic. Remember the philosophy about the steps one by one. Okay, so you have the finding with your damage. Check what type of damage you have. Check the exact location. Check for allowable damage. And then, if it's necessary, do some blend out, do some rework, maybe some protection you have to apply. Many times we just have a small dents, which are just like minor dents, but still you have to put it in the book. On every company there is a folder, and in this folder you can find different schematics from chapter 06. Let me show you just a second. So we're going to MM part 2, chapter 06, and then body station diagram, for example. So this is what you can find in this folder. Pages printed with these different point of views, okay, on the aircraft with all the zones, okay. So you can put here your damage. Your damages forward here of the forward cargo door, for example, and you have to mark your damage with something like a sequence number or sequence letter. It depends on the internal procedure. So it's not really regulated by authorities, as I know. There is not a specific name of this folder. Sometimes it's called damage chart, or dent and buckle chart, or repair chart, or damage assessment chart, or something like this. But the philosophy and the logic is the same. You have to mark your damage on the respective page, because also you have damage that could be on the wing. Yes, have wing. Yes, it could be on the power plant, it could be on the horizontal stabilizer. Yes, so you have to find your damage, your picture here, your schematic, to mark the damage location, and then in a table, which is part of this folder, part of this document, let's say, you have to explain in the table what is behind 37. You have to put that this dent, it's located in this specific position, for example, right hand side, on this distance from the tip, or this distance from the forward spar. You have to explain the exact location to show the dimensions also of the damage. If it's dent, the depth, the width, the length, everything which is necessary. And if you release the aircraft to fly with this problem, you have to specify where exactly in the SRM it was written that you can dispatch the aircraft with this problem. Let me give you one example. Usually this is something that we are doing during the practical training, but just very fast I will try to show you. Is that interesting for you? Like a logic?
Yes, sir. Yes, sir.
So slat skin, for example. This is for the wings, slat skin. So for the slat skin, you have this here, limits. You can find the thickness of each panel, and finally somewhere we can find the allowable damage. Just give me a second. This is for the slats 1, 2, 3, and 4. It shows the thickness of the slat skin and can be used to help in the analysis of the allowable damage and typical repairs on the skin. Just a second. Where was the allowable damage? Dent. Measure the maximum depth, minimum axis of dent, and maximum chord-wise length of the dent according to the figure, and use a table to find the necessary action. So, using this figure, you have an example how you can measure the dent and the different dimensions that you have to measure. And after you measure, then you can go back in the table and to find if this is acceptable or no. Top skin, no skin, bottom skin. So if it's a no skin, for example, let's say we have these sizes, maximum of 1 on field dent is acceptable. If there are more than 1 dents, make a fitting procedure, make a fitting procedure, make a structural repair, you see, depending of the size. Because once again, this is an example how on the same place we have the same type of damage, but because of the different dimensions, you have different actions, you see. One is just you can release like this, but let's don't go so much in details. My point is that finally, when you're releasing the aircraft, you have to put aircraft released according SRM part 2, page 2 on this reference, which is shown here on the top. Allowable damage 52, dent, table, for example, 102 or 101, top skin, blah blah blah. So later, if someone wants to check, it can easily find your steps, your measurements, and how you release the aircraft. Because I've seen many times damage which is referred to a general chapter 570000. this is not giving me any specifics how the damage was evaluated and if it's in the limit or no. Yes, so be precise when you are explaining, especially when you release with a law about damage. Okay, I don't know if this example was good, but my point is in the SRM you can find your limits. Okay, and let me go back here. These are standard procedures, okay? Standard procedures for evaluating the damage. You don't have to be shy or to be, how to say, worried. If you have no experience with this, ask your colleagues, someone to show you, to explain you, and one by one cases, you will become more and more experienced. At the beginning, it was a big shock for me when I have to investigate and to analyze, for example, damage. And I can tell you it was very difficult for me the first time. I still remember because it was a lightning strike. And during the inspection, I found some panels which were disbonded, delaminated on the pylon, and also I found some burn marks on the rivets, and some part of the rivet head was missing. But my colleagues, they show me the first time that we have limits also how much material from the rivet head could be missing. They show me some specific things in the SRM, how to work with SRM. And believe me, my first time was with PDF files. And as you can see from this Embraer software, it was very easy to browse in the SRM, correct? It was very friendly to find schematics, to find text, to find tables. Now imagine if you have to use a PDF files only, okay? And you are scrolling the pages on this PDF file. It was terrible. It was terrible. But with the experience, everything will go in position. So here we have a few words about the composites. Composite liquid detection standard procedures. We have, if you have one of these conditions, liquid contamination may have occurred. In these cases, we have to remove liquid according to SRM. Why the liquid is dangerous for the composite materials? Do you know that? Why? Why missing paint on the composite material? Why small holes in the composite surfaces? I'm not talking about holes which are penetrating the entire material. No, just a small holes here, like missing paint. Why they are dangerous for the composite material? Do you know?
Yeah, because it leads to delamination.
Why? How a small hole or missing paint will cause delamination?
Moisture can get it.
And what's the problem? What's the problem if we have moisture?
Each player crack together by the resin inside, so it moisture go to inside, lead to delamination of the.
Very well, very good. So the moisture as a moisture is not a problem. So imagine that we have some paint missing here. Yes, because of, I don't know, for some reason paint is missing here. And during the flight, not during the flight, on ground or during flight, of course, some moisture can go inside. Why? Because we have these composite materials, which are composite panels, which are manufactured, you know, from different layers. Different layers. We have core, we have like a skin, top and bottom, but it is possible moisture to go inside. It's okay. There is not a problem. the problem begins when the aircraft starts to fly, because the negative temperatures will make this moisture to become ice. And when the moisture, the water becomes ice, it increases the volume, yes? So the increasing of this volume will make here change of the cross section, and then this top coating or top panel or whatever will be not bonded anymore to the composite structure here. So we have delamination or disbonding depending of the type of the composite material. So for that reason, for example, it's critical if you have some damage on the, or paint missing on the radome, because the radome is, you know, the area which is in first contact with the air, and we always have moisture. It's raining, yes. So this moisture will go inside, not inside the radome, but inside the composite structure of the radome, and then first of all, this will affect the operation of the weather radar. This will affect the operation of the, I don't know, maybe the radio navigation equipment, the ILS antennas, the light slope, and so on. So that's why missing paint is very, how to say, dangerous for the composite structure. And there's something that it's very easy to be done to protect the structure until final solution is found. Maybe some repainting, or maybe some replacement of component, if it's acceptable, of course. We can put high-speed tape. We can put high-speed tape, and this will protect the whole, yes? But the high-speed tape, we cannot put just like this, okay? We have to consult with the SRM to find our damage, and if it's written that we can dispatch the aircraft with temporary repair, and the temporary repair is to use high-speed tape, this is how we can release the aircraft. And then you have to put the reference for the specific SRM which is asking you to do like this. I had a colleague who is very experienced, but he's very lazy. He's very smart, but also lazy. So on one engine, on Airbus 320, during inspection, during walk around, he found many, I'm telling you this and we go for a break. He found a big number of, how to say, paint missing on the thrust reverser panels and the fan cowl panels. Okay, a lot of spots with paint missing. So he decided to be professional and to cover these holes with high-speed tape. And because he is experienced, he knows very well that when you apply the high-speed tape, you have to make the corners rounded, okay, rounded corners. So he made very beautiful patches from high-speed tape, and he covered all this missing paint. But he didn't report it nowhere, not even in the logbook, not even to the customer, the operator, nobody. I mean, it's very good. It's a one very good-looking repair, but unofficial. Then there were audits from authorities, and they found these very beautiful repairs. And you can imagine that you have a white color of the engine fan coils and a silver high-speed tapes on multiple places. So they checked the logbooks, they checked the dent and buckle chart, or it doesn't matter what is the name of the document, or repair chart, and they found nothing about these repairs. And it was kind of internal investigation who did that, because we are many people working on these aircraft, and nobody is saying yes, it was me. Because if he says it was me, he is in a big troubles. Why? Because he did it according to the procedure. He did it perfectly, except it's not documented. So this is another example. Guys, please document it, okay? Everything is fine. Everything is legal, but like repair, it's very skillful, but please document it, okay? This is important because I can give you another example. On one engine, one of the blades had some dent, my favorite flowers. There was a dent, just this one, and someone made a circle around the dent and he put okay. So most of the difficult job he did. He found the damage, he consulted the SRM, actually for the fan blades, the aircraft maintenance manual, sorry, AMM. He do the measurements, everything was fine, it is in the limit, no restrictions, the engine can continue to operate like this with this fan blade, but there's nothing in the book, okay? There was nothing in the book. And when you're doing walk around, especially the flight crew, they see the dent, the circle, it's written okay, and they think that someone already investigated this damage, okay, assessed the damage, everything is fine. But nobody is checking the book, if it's in the book. And finally, again, the authorities, because it's obvious, you're looking the fan blades and you see a circle, you see okay with permanent marker, and then you're interested to find out when this dent appear, yes, on which date, and what are the dimensions, and according to which document it is acceptable to fly. Nothing in the books, okay? So please be professionals, and this is example how the people, they care about the safety. They care about the safety, they did the measurement, they did the assessment, but finally they were kind of lazy to make it official, okay? Because there are other group of people which they just check the damage with their, you know, like eyes, which are scanners, and they say, oh, this damage is in the limits, and they just close their eyes. Please don't do it like this, okay? Because some people are saying, oh, this is a very small dent, no need to investigate it because I know it is in the limits. Yes, you know it is in the limits, but please make it official. So the next guy will find the same damage. The first step will be, okay, there's a dent, I have to evaluate it. But before you start to evaluate, check the book. If it's already in the book, no need to waste time, correct? This is another reason why we have to mark all these dents in the book. Okay, guys, this was something like a standard practice for the structure, and maybe I put more attention on some examples from the real experience that I have. But the point is, once again, to be careful when you are identifying the damage, the type of the damage, to be precise with the lowable damage table, and then to be precise with the documentation filling. Of course, also with the structural repair work if it's necessary. But here I was talking mostly about some repairs that we do in line maintenance environment, just easy repairs with just some, you have to apply paint or primer to protect the structure against corrosion, maybe to apply high-speed tape, because as I told you, when we have to talk about some skin repairs or some other repairs, well, we need professional for this, okay? For example, I don't feel skillful to do repairs like on the skin, like on the fuselage or whatever, okay? They are professionals which were studying how to do these repairs, and I'm professional which I was studying for the systems, yes? And here you have the examples for specific damage that can appear on composite structure. Delamination, disbonding. You see, the delamination and disbonding, they look like the same. You see? But actually, they have different explanation. A rising of the surface above the horizontal level may indicate an interply or skin-to-skin separation. A rising of the surface above the horizontal level may indicate a skin-to-core, okay, separation. That's why I told you, delamination and disbonding they are kind of the same. It depends of the type of the composite material that you have. This is the sandwich panel, yes, with top and bottom plates. This is just composite materials with many layers. Okay? So, do you have any questions? No? Okay, let's have a break then. And later we are going to continue. Next one is fuselage, chapter 53. So here we are going to talk about the different fuselage sections and about the structure, fuselage structure in general. Not only in general, but also in details. So the fuselage is the main portion of the aircraft to which the wing, horizontal stabilizer, vertical stabilizer, they are attached. Also, we have the components of the systems attached to the fuselage, including the APU, which is in the tail cone. The fuselage structure is shell type. It's a double bubble. And, you know, it's a provide accommodation for the crew, passengers, cargo, and some system components, structure, and so on. It's a semi-monocoque type structure, and most of the structure is aluminum alloys. As I said, it's a double bubble section, and we have skin panels to resist to the pressure loads. And the main components you already told me before the break: stringers, frames, skin, ribs, and we have, of course, additional structural elements, but the main components on the structure are stringers, frames, and skin. Embraer, when designed the aircraft, they calculated that the integrated life of the aircraft will be approximately 80,000 flights, or approximately 80,000 flight hours, sorry, or approximately 60,000 flights, like cycles. And the components of the fuselage are floor panels for the cabin and cockpit, also on the cargo. We have wing to fuselage fairing, which is composite panel, providing aerodynamic shape on this wing to fuselage junction. Also is protecting some components, you know, in this still unpressurized area in the below the lower fuselage. And then the fuselage is divided in forward, center, rear fuselage. Okay, have a look. We have different sections which are coming together. Okay, you know, the fuselage is not one assembly, but is composed by different sections. And now we are going to talk about these different sections. So, have a look. The fuselage has the following main sections: forward fuselage, center fuselage, and rear fuselage. Forward, center, rear fuselage, and tail cone. In addition, the center fuselage is divided on 3 sections: center fuselage 1, center fuselage 2, and center fuselage 3. Okay, one more time. We have forward fuselage in general, center fuselage in general, and we have rear and fuselage and tail cone. But center fuselage is divided in 3. In addition, only for Embraer 195, center fuselage 2 is divided on 3 additional sections. So it looks like confusing, but it's actually very simple. We have 3 big sections on the fuselage, on the center fuselage, and only for Embraer 195 we have 3 more for the center fuselage too. Okay? Is that clear? This is important to make the difference between the different sections. Okay? Good. Here from this schematic, you can find the different frames, location, and one advice when you're evaluating damage, always look for a reference point. If you find a damage, let's say here, it is not necessary to count from frame number 1. To count 1, 2, 3, blah, 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 to reach this section, which is between 26 and 27, yes? Because you can make this mistake. You are not sure exactly where is it. So find a reference point. In this case, I would, if I have to do some evaluation, I will use the windows, the passenger windows. When I count the windows, the first, the second window on the left side, so I will check this schematic and I will see, okay, my damage is between the windows, passenger windows 2 and 3. I will cross-check and I will see, okay, between frame 26 and 27, this is my damage, and this is exactly between the second and the third window on the left side. Do you understand what I mean? Or if your damage is here, of course, no need to start from the first frame. Just have a look. We have this escape hatch, okay? The escape hatch is between this and these frames. So, okay, one window behind, I can find easily the frames by using a reference point. This is to avoid mistakes or to reduce the possibility of mistakes when you're finding some location. When you talk about floor panels, they have to resist the crew and the passenger foot traffic, also service cards. Also, we have galley units. We have some baggage compartments in the cargos also. And the panels, they provide structural coverage, underflow system protection, and they are noise abandonment in the cabin. The panels are divided into the passenger cabin floor panels, cockpit floor panels, and we have cargo floor panels. We already talked about the cargo compartment yesterday. The passenger cabin floor panels are honeycomb sandwich composite structure. Honeycomb sandwich panels with unidirectional graphite plies. 2 types of panels are used in the passenger cabin. One of the panels are located in the center aisle and the entry area, and the other panels are located under the passenger seat. You understand that the center aisle and the entry areas, the panels, they have to be a little bit more stronger, more resistant to the heavy traffic, because everybody are walking all the time in this center aisle. But below the passenger seats, we don't have such a traffic, okay? We just are using the floor panels just for our legs, where it's not our weight, just our legs are hanging. Our weight is actually on the seats, And in addition, we have different type of panels which are because of the different density core. And this is especially above the forward avionics compartment and the middle avionics compartment. Because all this avionics equipment below has this electromagnetic interference, okay? They are emitting electromagnetic waves. And Embraer, they decided that they will provide specific panels with electromagnetic interference shielding to protect the passengers and flight crew from this avionics equipment. Okay, so above the avionics compartments, we have these specific panels, which has aluminum foil over the graphite layer for protection against, once again, these electromagnetic waves. When you talk about the cargo compartments, you know that we have specific panels, we have flat panels and curved panels. We also checked yesterday some restrictions for some kind of damage, and yes, they're specific. Also, the cargo floor panels, they have a top coating, top surface, which is like a sandpaper, which is preventing slipping of the luggage, if you remember from yesterday. Okay, we have different number of panels, 9 panels in the forward cargo, and 7 panels in the aft cargo. Well, this is not mandatory to know it. Just keep in mind the different types of the panels, okay? Have a look. Cockpit panels, because below we have forward avionics. Here in mid cabin, below we have the middle avionics compartment. Again, the aisle panels in the cabin are a little bit more specific because they are high loaded. Same with the forward and the aft galley areas. They are a little bit more specific. The panels which are under the passenger seats, they are not so resistant to the weight. Okay. Wing to fuselage fairing. Wing to fuselage fairing is between frame 35 to frame 74. Composite materials and providing aerodynamic shape in this wing to fuselage junction. Also, as we said, it is covering the components from many different systems which are below the fuselage, but you know, above this wing to fuselage fairing. Composite material, carbon fiber, and honeycomb. We have fasteners, internal ribs, supports, which are made of different materials, mono, aluminum, and titanium alloys. Keep in mind that, like in general, this supporting structure of the wing to fuselage fairing, it's not primary, it's a secondary structure. Okay, it's a secondary structure which is keeping this wing to fuselage panels. All fairing panels, as we said, are made of carbon fiber Nomex epoxy sandwich panels. And we have difference between the different panels. We have totally 3 big panels: forward panel, center panel, and the aft panel. It is very difficult job, believe me, when for access you have to remove these big panels. You can imagine that we have all this yellow here is our wing to fuselage fairing, this belly fairing, and it divided only on 3 panels. If you want me, I can zoom a little bit so you can see the number of the screws here. You see, it's terrible if you have to remove, really, it's too much. Well, if you're working in base maintenance in the hangar, you have everything you need. You have this pneumatic tools. You can much easier disassemble these panels. Also, you know that once you remove the panels, you have to install only after you finish with the entire base maintenance tasks. So it makes sense to put some efforts to make access. But in line maintenance environment, I have experienced 1-2 times, it is terrible. So what is the specific between the different panels? The forward panel is covering the air conditioning pack components, environmental control system components, as I said. Slat PDU, we have the ground connections for the high pressure and low pressure. and we have two NACA air inlets. These two NACA air inlets are actually the inlets which are for the air conditioning packs, for the cooling of the heat exchangers. If you remove the center panel also we have some components from the air conditioning packs related with the outlet lower. I'm talking about the duct, this ram air duct. We have access panel for the aileron control mechanism. We have hydraulic system components, and also it's covering the wing stop region. Also, on this center panel, we have the lower red beacon. And we have these brush assemblies. These brush assemblies are actually as part of the fairing, but you know, when the gear is retracting, the wheels are brushed here. The wheels are brushed, and if there is any kind of how to say, dust, moisture, water, something like this, it's actually kind of sealing the compartment between the fairing and the wheels, but also it's cleaning if there is any unwanted dirt on the wheels. Nothing so special, but this is the function of these brush assemblies. Okay, what else? The aft panel. The aft panel is covering the hydraulic system components, ecological bottles, flap PDU, which is inside, you know, the mid avionics compartment, and actually the door, which is for the middle avionics compartment. This is below the aft panel. And all these three panels are between frame 35 and frame 72. Okay, composite panels, three pieces. The differences between 190 and 195, I already told you. And once again, they're coming from these different plugs, which are increasing the length of the fuselage. You can see here. Okay, in Embraer 195, we have, once again, forward fuselage. We have the center fuselage, yes, but the center fuselage was divided on three, yes, 1, 2, and 3. So you can see these plugs size, and then comparing to 195, the center fuselage section 2, as I told you, is divided on 3 sections. This forward section, the part one is extended, and also part 3 is extended. This section 2 is same. And as I told you, when we are talking about center fuselage for the Embraer 195, the center fuselage 2 is divided in 3 additional plugs. Okay, have a look. A and B. It is here. Center fuselage 2 is divided in 3 primary groups: front, middle, and rear. Okay, please try to remember this like a difference. I don't know if you're going to have Embraer 195, but this is specific when we're talking about the center fuselage 2. Okay, and here we have the details between which frames are extending these different plugs. No need to remember, just keep in mind that we have specific frames for each specific plug. Okay, this is the difference now. Forward fuselage, from frame number 1 to frame number 20. Semi-monocoque structure, conical and double bubble cross section. We have skins, frames, stringers, and we have longitudinal transverse floor beams. So guys, from now on, we're going to talk about these components: longitudinal and transverse floor beams. Okay, including to the addition to the skins, frames, and stringers. We're going to put some attention about these sections and the primary structural components. In addition to this forward fuselage, we have cutouts, which are for the passengers, service doors, passenger windows. We have this forward fuselage divided in two parts, which are upper forward and lower forward fuselage. Let me show you. This is between frame number 1 and frame here 20. This is our forward fuselage. And this forward fuselage, as we said, is divided on lower and upper. And you see that we also have openings for the pilot windows. We have opening for the nose landing gear wheel well. We have a nose landing gear wheel well box. We have also some, let's say, holes or openings for some smart props, total air temperature sensors. We have also this small door, which is for the external power receptacle. Okay, these are all located in the forward fuselage. We have different type of frames. They are manufactured in different way. We have I-formed and C-formed shaped frames, and they have different way of manufacturing. I will try not to go so much in details because I'm afraid that I'm going to lose your attention, because I have to repeat all the time these different types of frames, which are more or less the same. But at the beginning, I will give you some information, and then I will just mention this type of frames. So these I and C form shape frames are directly attached to the skin, or they are attached with shear clips. These shear clips is allowing the stringers to run to the full length of the fuselage. And this is like for the majority in a typical fuselage sections. So for the rest of the fuselage, it will be almost the same. We have some exceptions, of course, but it will be kind of same. These machined C-shaped frames, which are directly attached to the skin, or they can be attached also with shear clips. Same story like the previous one. So you know what is the C-shape frames? The shape is like this, C-shape. We have I-shape, we have T-shape. Give me a second. Okay. Okay, I'm sorry. So the forward fuselage has 4 types of splice joints. They have some differences, structural differences, of course, and have a look. I think we have a picture for that, or no? Okay, so we have just 4 different types of joints, okay, with different splices. Number 3 and number 4 are with different splices, and number 1 and number 2 have this direct attachment with both flanges, which are attaching to the web. These splice joints are actually making different sections coming together. Also, we have skin panels, which are on the forward fuselage section, 20 skin panels with stringers and shear clips, made of aluminum sheet, manufactured with chemical milling at the pockets between the stringers and the frames. This chemical milling is protection against corrosion. And when you talk about the skin panels, they are padded up around the cutouts and reinforced locally by doublers, which are distributing the stress of the corners. Because we have several cutouts, as I told you, for the pivot windows, for the nose, landing gear wheel well. So this reinforcement is to increase the resistance to stress, especially when you talk about the corners. You know that initially, when the aircraft starts to be designed 100 years ago, the windows, they were square, and later they found that in the square windows here on the edge there are cracks, and with the experience in the service of the aircraft, these cracks increase and suddenly the fuselage is separated. That's why now we have rounded windows, rounded cutouts, because there is no stress here, there are no corners. Okay, so in some places we have to increase the strength of the structure, especially where we have cutouts, and this is done by doublers most of the times, as it is written here. So the skin panels are joined with the skin splices of the butt joint type. Stringers, we have some specifics when you talk about the forward fuselage, because we have 28 stringers on each side, on the section at frame 20. Then we have 17 stringers when we're at frame 5, and 13 stringers on each side when we talk about frame number 2. This is because here, you know, the stringers are passing like this. Yes, they're straight, but as you can see, the cross section is changing here. So as forward we go, the number of the stringers is reduced. So finally here at frame number 2 we have 13 stringers. Okay, the stringers are manufactured with aluminum extruded Z-shape section, and they are riveted to the skin. This is what we call double bubble construction. Double bubble, it's like one bubble is here on the upper area with one diameter, and we have another bubble with lower diameter here on the lower area. How we count the stringers? We have the 0 here just at 12 o'clock on the top, and then starting to count left or right, we increase the number, like 1, 2, 3, 4, 5 right, or 1, 2, 3, 4, 5, 6 left. Okay, until we reach here stringer 28 left and 28 right. This is how we number the stringers, just to have an idea. And if you have a look at this nice picture here, you can see the structure. You can see the frames, you can see the stringers, you can see here the cabin floor structure, these beams and spars, sorry. You can see the cutouts. Forward entry door, forward service door. Here we have this opening for the flight crew windows. We have one passenger window here. Okay. In addition, when you talk about the lower area, I'll show you another openings. This is example of the Z-shaped stringer. You see, it's like the letter Z here. This is the typical stringer cross section. Upper forward structure, have a look. Longitudinal and transverse floor beams. Transversal frames we have, and longitudinal stringers. This is our forward fuselage. And also on the forward fuselage we have the pressure bulkhead. I don't know if you remember, on the very first day I put attention on this. On this aircraft, frame number 1 is part of the unpressurized area. Frame number 2 is our forward pressure bulkhead. Okay, the forward pressure bulkhead. And to be honest, I totally forgot about this after my type training, but in my experience, one aircraft arrived after lightning strike, but the lightning strike was on other airport, so they flew back with passengers to our airport, and during the walk around we found one hole, just a hole here at 6 o'clock, just behind the radome. And we already had this frame number 1, yes, just behind the radome is frame number 1, then number 2. So I said, oh my god, this is not possible. They were flying like with a lot of air leaking, because the hole was big, so I can put my finger there. My finger I can put in the hole. It was amazingly big hole because of the lightning strike. Well, when we opened the radome, we were so happy that actually the pressure bulkhead was starting from frame number 2, because our hole was just between number 1 and number 2, and it was actually non-pressurized area. Okay, otherwise there will be a severe air leak from there, and actually the pilots, they were really happy people, really lucky people, because when they were hit by lightning strike, they didn't ask for maintenance to check the aircraft, but they decided that it was not a strong lightning strike, so they just performed a walk around and everything was fine, they said. But actually during our inspection we found many damages. So later these pilots were reported to the authorities because they were acting like criminals. But this is a different story. Let's go back to the structure. My point is that this is something specific, because on other aircrafts that I know, usually the forward bulkhead starts with the first frame. But here, between frames 1 and 2, we still have unpressurized area. Number 2 frame is our forward pressure bulkhead. And as I already told you, we have different openings here from the forward upper and forward lower fuselage. So we have one passenger window, forward passenger door, forward service door, flyback, windshield frames, direct vision window frames here for the windows, as I said. On the lower fuselage, we have the forward avionics compartment, forward cargo compartment, ram air turbine here, and nose landing gear wheel well. These structural zones and components are part of the forward fuselage. The forward pressure bulkhead, as I told you, it's starting here from frame number 2, and consists of pressurized flap web manufactured from chemically milled aluminum sheet. Okay, I'm sorry guys that here I'm kind of reading this material, but this is not something that I can explain, or I can, how to say, improvise. I can use different words. These are specific structural words, specific structural terminology. So to be correct, I have to use this specific terminology. Okay. So again, we have C-shaped aluminum cross beams here. This is also specific for the cross beams. Most of them are C-shaped. Okay. Especially for the floor structure, cabin floor structure. We have horizontal straps manufactured from aluminum sheet on the top of the beams to transfer the tension and the bending loads to the cross beams and vertical beams, yes. Cockpit floor structure, cabin floor structure, have a look. Beams, longitudinal beams, cross beams. This is our floor structure, and here you can see one openings here like a brackets, not actually brackets, but yes, like a brackets here, which are aileron control support, because here we have like a guide. This is the root of the aileron control system components. You know that they're not only just cables passing through, but on some places we have also pulleys, we have quadrants, So we need some attachment points for these components. And as I told you, and you know from the flight control system, some of the cables are passing below the cargo floor, and some of the cables and components are installed below the cabin floor. Okay, this is how the forward pressure bulkhead looks like. The main components are this web, as I said. We have cross beams, we have straps, we have vertical beams here, fitting angle ring, and we have these intercostals. Very interesting component is this intercostals, like a name. Lower forward fuselage, have a look. I'm not going in details with all these numbers here to tell you all these frames, okay, one by one. I just want to focus your attention on the main structural components and which components you can find actually in the different fuselage sections. So here, when you talk about the lower area, as we said, we have the opening for the forward avionics compartment. Here we have these electronic racks, yes, and this electronic rack is another example for secondary structure. It's not a structural component which is accepting any kind of heavy loads, pressure loads, or this is just a rack keeping the avionics equipment. This is kind of secondary structure. Nose landing gear structure here, this is our nose landing gear wheel well. Okay, and here this is where the aft cargo compartment, the forward cargo compartment starts. Here, looking from forward zone, this is our opening for the ram air turbine door, and again you can see here the forward avionics compartment and this nose landing gear wheel well box. This is looking from outside, from the lower part, and this is here looking from inside. It looks like this. Do you remember what I told you about the cargo partitions? The forward cargo, in the front end we have partitions, this forward bulkhead of the cargo, and I told you if you remove the panels you can climb here over the nose landing gear box, or you can go around the box. Once we have a structural damage, I told you just below the captain's window, just a little bit lower, and it was necessary to go inside. It was not a good place for me. Radome. Radome is a composite structure, glass fiber skin construction with Nomex core honeycomb. Do you remember the Nomex? What was the Nomex? This fireproof layer inside the composite materials, which is also protecting against fire. If the core is not damaged, it will resist to high temperatures or smoke. It's actually isolating the surfaces, the two different surfaces of the panels. The radome is hinged on the forward pressure bulkhead, opens upward, and we have access to the weather radar, the light slope antenna, and the outside part of the forward pressure bulkhead structure. The radome attached with form arms, and we have brackets, interconnect the brackets with the pressure bulkheads. We have arms which are part of this hinge mechanism. Actually, let me show you here on the picture. It's much easier. We have the bracket, we have these arms, so we are opening the radome up. We have tap, which is kind of secondary structure to connect this bonding jumper. bonding jumper, which will transmit this accumulated static charge from the radome surface to the structure, to the fuselage actually. Have a look. This is our fuselage in open position. We have a polyurethane film, which is something specific for Embraer. This polyurethane film is transparent and is protecting against erosion, against abrasive erosion, because as we discussed several times, the radome nose is the first point of contact during flight. So we said that in the air there are always some particles, some small particles, which are actually accumulating the static charge. But also these particles, they are making this erosion on the paint and on the surfaces. So you can find these polyurethane films on the wing leading edges. You can find on the vertical, horizontal stabilizer also leading edges. This is erosion protection. The problem is that this polyurethane film is getting worn during the service of the aircraft, especially because of the sun, because of the cold, and it starts to separate not pieces, but yes, some pieces of this layer are separated, and we have to repair. And the repair is something, how to say, not so difficult, but it takes time. Because first you have to remove the entire polyurethane film, all the remaining pieces. Then you have to clean very well. Then you have to apply some adhesive materials and to apply the new polyurethane film. And it takes time, and yes, it just takes time. It's not just a so heavy job. And there are some restrictions and some limitations in the aircraft maintenance manual when you talk about this polyurethane film. So let me go back here to the radome. We have a rubber seal which is sealing here the gap between the fuselage structure and the radome, the cone, to prevent any moisture to go inside. For maintenance, we have two hot open rods which are keeping the radome in open position, as I said. And you can find the weather radar, you can find the glide slope antenna. And once again, let me go back to this static charging, these particles which are making erosion. Because they are accumulating charge, and radome is also one of the most popular zones for lightning strikes. Okay, usually the lightnings, they hit the radome, they hit the inlet, the leading edge of the components, like the wings leading edge, like the vertical or horizontal stabilizer leading edge, or the inlet of the engine, because once again, this is the zone where we have kind of accumulated charge. And to provide better protection of the radome, we have these lightning strike diverters. On other aircrafts, maybe you've seen like strips. So these diverters, they are transmitting the accumulated charge on the radome to the structure. And this is possible through the through this bonding jumper. Okay. So what else? And as I told you, please, when you're protecting the radome, because it's composite, if you find some paint missing, and to avoid additional damage, we have to protect. And one way is if you use this polyurethane film, but also there is another specific tape. I don't know the real name or the manufacturer, but like in general, we are using the name like a radio transparent tape. This is a tape which is protecting the surface, but at the same time, it's providing this radio signals transmission. it's not affecting the transmission of the radio communication. That's why it's called radio transparent, or at least here in my country and my colleagues we're using this radio transparent tape. Please, please do not use high-speed tape here, okay? High-speed tape is aluminum foil, you know, and it's a metal foil which will affect the operation of the weather radar. Actually, it can cause damage to the weather radar system. Also, it will affect the operation of the glide slope antenna for the ILS. So please, especially for the radon, for protecting composite, do not use high-speed tape. Yes, it is approved in the structural repair manual to use high-speed tape on the belly fairing, this wing to fuselage fairing, on the slats, horizontal, vertical stabilizer, it's okay. Fuselage skin, okay. But here, please, only special specific tape, radio transparent tape. Once again, maybe the name is not the correct one, but the important is the function. It should provide normal transmitting of radio signals. Any questions here for the radon? I forgot to mention that we have 4 quick disconnect latches. So radon has 2 support rods, hot open rods for maintenance, 4 quick disconnect latches, and it's hinged on the top. Next one is it time for break or not yet? I think not yet. We have 10 more minutes. Yes? Give me a second. Okay. We have 10 more minutes. So let's continue with the center fuselage. We already know that is divided on 3 different sections: center fuselage 1, center fuselage 2, center fuselage 3. They're covering different zones, but if I have to go here in details, the main function is to provide accommodation for passengers and crew, room for baggage in the overhead bins, and also in the forward and aft cargo compartments. Here is what we can find when you talk about the center fuselage. Passenger compartment, cargo, this is passenger from the top, forward cargo, aft cargo. Here we have the wing stub, okay? So one by one. Center fuselage 1 is between frame 23 to 34. Skins stiffened with stringers, transverse frames, longitudinal and transverse floor beams. We have cutout for the cargo. We have cutouts for the passenger windows, many of them. We have brackets and supporting structure for the overhead bins, floor structure, and some system equipment. Have a look. Again, we have this transversal frames. We have longitudinal stringers. We have longitudinal and transverse floor beams. This is our support structure for the cabin floor covering. As I said, passenger compartment is in the upper fuselage, including the cabin windows. On the lower fuselage, we have the forward and aft cargo compartment. These are the brackets which we need for the cabin windows. Okay, these are our support brackets for installation of the cabin windows. Have a look. So this is the the brackets here for installation. When you talk about the windows, I think it's tomorrow, you can see the installation picture, and you will see how it looks like with a little bit better schematic, if I'm not wrong, but I think it's like this, yes. So we have 12 circumferential frames on the center fuselage one, and there are two different type of frames: typical frames, type 1, and type 2 special frames. And now I'm going to explain you in simple way why we have this difference: typical and special frames. The typical frames are made of U-formed sheet, and the special frames here are machined, including lateral C-track support and shear clips. Just let me show you on the next schematic why they are different. Machined frames. Okay. These machined frames, they are making this double bubble section. You see, they are making like a circle. But on some places, we don't have this complete circle. And these places are where we have, for example, here, what we have here. Do you have an idea? This is forward. This is the forward cargo door. So it is not possible structurally the same frames to be used here, because their construction, their design is just to come one to another and to make this shape of the double bubble structure. But here, where we have these cutouts, we have to interrupt the strength here, the frames. That's why different shape of frames are used, and there are different types actually of frames. That's why they're called special frames. Later you'll see another locations with special frames. Okay, so have a look once again, because here the explanation is how to say, not really understandable, because they are using so detailed this structural terminology, which is not really acceptable sometimes. So my easy physical explanation is that in these zones we have just the same structure. We have no change of the size, no change of the diameter. Just we have some openings, and they are requiring, as you can see, some machined frames. These machined frames are much more stronger, because here we have different loads, and the strength of the structure must be increased. Everywhere where we have a cutouts, if you remember when we talk about the forward fuselage, near to the cutouts we have like additional pads to resist the stress in this zone, also to reduce the possibility there of some cracks, and during the cycling of the aircraft during the service. Here, when you talk about the center of fuselage 1 and this forward fuselage section 1 junction, we have these splices. The splices is the component which is making two plugs coming together. So here on one side we put one plug, okay, and on the other side of the splice another plug continues. Okay, these splices are used. Longitudinal stringer splice, and we have here orbital skin splice. Okay, this is the component which is making these different plugs coming together. And as I showed you, this cargo door frame must be with increased, so it must be reinforced to resist the loads here. You know that the doors, they have, tomorrow we're going to talk about the doors, but you know that the doors, they have door stops which are transmitting pressure loads to the structure, and it's not the same if the pressure is transmitting the load to the skin it's one story, but like here, we have the internal pressure, which is pressurizing the aircraft, yes. It's transmitting the load here to the skin everywhere. But here, where we have cutouts for cargo doors, for passenger doors, for hatches, we have to reinforce the structure to be much more stronger. When you talk about center fuselage 2, it's between frame 43 to frame 59. This is what we have. We have the upper cabin zone, we have emergency hatch here, passenger windows, passenger floor covering, but also we have part here of the avionics compartment. Here below we have the wing stub, and again the structure here is a semi-monocoque. The panels are stiffened by longitudinal stringers and transversal frames. Same structure, more or less. But in the lower section, again, we have these machined components, and now we're talking about the machined pressure bulkheads. Machine pressure bulkheads because they are isolating the wing stub from the cabin pressurized area. The wing stub and also this well compartment. Also, the middle avionics is located there, this central electronics bay, and that's why we have these big cutouts here. That's why we also need specific frames, which are, just a second. No, they are not shown here on this picture. Okay, anyway, so these different plugs, which are specially for Embraer 195, remember? With this additional marking, center fuselage 2, plug A, center fuselage 2, middle plug, and center fuselage 2, plug B. Again, not necessary to remember all these stringers and these frames which are here. Just remember that in Embraer 195, the center fuselage 2 is divided additionally to 3 different sections. The structure is the same principle, like components, like organization of the structure. Again, we have stiffened panels for the skin, longitudinal stringers, transversal frames, beams. Everything is like on the previous section, just we have now different cutouts, okay? And these different cutouts, like different plugs, are shown here. Just a second, okay? Here, B and A. Okay. What else? Stringers. Stringers in that area are shown like different here in the different zones. Aluminum alloy extruded segments with 7 different shapes. Why the shape is different? Because they are passing through different locations, and these different locations, they have some specific structure. And this specific structure, as I said, is because of all these openings and because of the different compartments. We said we have this wing stub, we have the avionics compartment, we have this cabin zone, upper fuselage of this plug. So for that reason, they are different type of stringers. As you can see, there are many numbers here. I'm trying to reduce this information for you, okay? Because it's really not necessary. This is information that is not helping you in maintenance. This is information that you can check anytime in the maintenance manual, correct? So keep it simple. And here you have again the numbering of the stringers. I already told you the previous session before the break. 0 is here on the top. and then we start on the left and the right side, counting, starting from stringer number 1 until we reach here 28 left and 28 right at the bottom at 6 o'clock. Pressure flood bulkheads, Q beam, and the middle avionics compartment. As I told you, we have some specific years. These two pressure bulkheads are related with this pressurization and the wing stub zone. This is to isolate the pressure area from this wing stub. Forward and aft flat pressure bulkheads machined from aluminum alloy plates, and they're attached at frames 45 and 56. The bulkheads are attached to the fuselage skin with wing spar 1 and 3 and to the Q beam. Just after a few seconds I'll tell you about the Q beam. Middle avionics compartment, we have opening between frame 57 and 58 and between frames 23 and 27 left. So we can access the avionics compartment. Again, we have specifics there because the avionics access door will transmit pressure loads not to the skin but to the structure, and that's why the surrounding of the door opening is reinforced. It's forged aluminum machined frame, auxiliary stabilizers, shear clips and angles. As you can see, it's not a standard structure like on the skin panels. We have one big aluminum doubler which is attached to the skin external side. Once again, we have specifics. Q beam. Q beam is attached to the center of fuselage 2, middle, and the wing stub to give the fuselage load path continuity to the wing stub region. You understand what is the purpose of the Q beam, yes? Because the structure, the shape is, you see the structure here? It's like, okay, let me try to simplify. Just to put your attention about the Q beam, what is the function? In this zone, this here, in this zone, looking from the side, we have like this, yes? It looks like this, actually even more. So you understand that if we have some aerodynamic loads on the tail section, the wings, here very easy, the section will break. For that reason, we have the Q beam. The Q beam will support and will keep here the strength of the structure. I don't know if you have experience, but one time I was flying Airbus 321 in the very last row. So during the takeoff and climb, I was looking the cockpit door, and it was like the cockpit door was moving left, right, up, down. This is because the entire fuselage was shaking, and it was shaking because here in the middle it's much more flexible. If you can imagine that there is no Q beam with this kind of aerodynamic loads, the aircraft fuselage will just break in two pieces. Okay, so the Q beam is very important structural element which is connecting the wing stub and this center fuselage 2 to give this fuselage load path continuity through the wing stub region from frame 43 to frame 74. The main structure has machine parts with cross-section, with head cross-section, and two machined side webs connected through 13 machine ribs. The side webs are stabilized using longitudinal integral stiffeners, and all the head section, the two side webs and the ribs are made from aluminum alloy. We have some machine parts which are called buff tub fittings, reinforced each end and the head section. So this is our Q beam, this is the head section, that is something specific here for the Q-beam. We have the left and the right webs here, and inside we have ribs. Ribs, and these are our fittings. The aft fittings and here forward. This is the component here, which is keeping the integrity of this center fuselage. These are our bulkhead assemblies. Bulkhead head assemblies, which are actually covering here and making the cabin pressurized, but not on the forward cabin and aft, but here near to the wheel well, here in this center fuselage area. And in addition, because the door of the middle avionics compartment is also in this zone, as I told you, we have reinforcement here with skin doubler. In addition, the hatch is reinforced, and can you see here, the surrounding structure is kind of specific, and this is to provide us once again accommodation for this hatch. This hatch has to keep the avionics compartment pressurized, yes, which is part of the entire pressurized fuselage. And because we have several different stubs, we have different yes, like plugs, we have these junctions, and we have these specific junctions between frames 59 and 74. The sections are joined in the butt joint configuration with orbital skin splices and stringer splices. The same type like we discussed between the forward fuselage and the center fuselage section 1. Have a look. Now, very nice picture here of the center fuselage. This is our wing stub. This is where the wings are attached. This is where our main landing gears are retracted, our main landing gear wheel well bay, and you have a nice picture showing you the frame, showing stringers, showing all this secondary structure here. You can see the seat tracks for the cabin floor. We have the beams, okay, the tracks, very nice picture. In the bottom, you can see on the lower fuselage, sorry, not the bottom, but the lower fuselage, you can see the pressure bulkhead, okay? The forward one, the aft one is located here, like this, okay? Wing stub area. Okay, we have one option, dorsal radome assembly option, which is for example, some additional equipment like satellite communication or maybe Wi-Fi service. So for that reason, this part of the upper fuselage have to be, how to say, we need a hole, and this hole have to be reinforced here with this dorsal radome assembly platform, and then we can put some antennas, as I told you, for satellite communication, for mobile communication, or maybe some Wi-Fi antenna or whatever. But this is really optional. By the way, I've seen one of these modifications in progress in Central America, because I told you some customers there, they put in-flight entertainment in their Embraer E190s, and the people are paying for this. You know, the passengers, they pay for using, for example, internet on board. And let me finish with the center fuselage 3 and we go for a break. So, same construction like the center fuselage 1, double bubble cross section, semi-monocoque. It extends from frame 74 to frame 90. Again, we have skins stiffened with stringers, transverse frames, longitudinal and transfer floor beams for supporting the floor panels. Of course, we have secondary structure like brackets, supporting structure for the overhead bins, and some additional equipment. The frames here are U-shape, okay? And we have also these cutouts, which are for the aft passenger door, aft service door, and for the aft cargo door. Here on this schematic, very similar to the forward, to the center fuselage one, very similar. Passenger windows, openings, stringers, frames, and floor beams. Standard structure, nothing so special. The only special is here when you talk about center fuselage 2, because we have many differences here in the construction. Keel beam, we have the wing stub, additional half pressure bulkheads, you see? Below the floor structure, we have many differences. Okay, do you have any questions here on the structure?
No, sir, everything is perfect.
Okay, we'll
No,
see.
so far so good.
By the way, once during training, one student like you, he told me there are so many numbers of frames, stringers, different sections, every zone, every plug, every frame, so different. I can't remember different shapes of stringers, of everything, you know, frames, machined, milled, protections, blah blah blah. And finally, he said after the exam, but there was only one question. I said, yes, it's 1 hour training for this chapter, it's one question. He said he studied so much, and finally, because of one question, he said, probably there is a big chance just to answer because I have knowledge during the lecture, and because it's not really possible, guys. I told you, that's why I'm trying to save this information. It's not really possible to remember all these frames. Actually, it's not needed to remember all these frames and sections, okay? So keep it simple and pay attention on the major differences that I'm putting your attention, okay? Let's have a short break and then. So again, here we have specifics. The rear fuselage extends from frame 90 alpha to frame 100, which is the pressurized section between 90 and 90 alpha. Now I will show you. A non-pressurized section is from frame this 90 alpha, 91 to section 100. The rear fuselage is semi-monocoque structure. We have again skins, transverse frames, stringers. We have two cutouts for the horizontal stabilizer, one cutout for the rear fuselage access door, and some brackets and supporting structure, secondary structure for system and equipment. And we have two different configurations for the floor covering, for the floor structure. One is the floor structure, which is part of the pressurized section, actually where we have the aft avionics compartment. It's part of the pressurized zone, just behind the aft galley. And another floor structure we have in the unpressurized fuselage section. This is for maintenance in the THS compartment. Okay, so have a look. Have a look. Here is the aft pressure bulkhead. This is our frame 90 alpha, and between 90 and 90 alpha we have the aft avionics compartment, and then between 90 alpha and number 100 we have unpressurized zone. And as you can see, we have changing here of the shape of the fuselage, and in this area we have this machine frame upper segments, which are really specific. For every frame we have specific frames, once again because the shape and the size, of course, of the of the structure is changing. So have a look. We have formed frames on the lower part, and we have machined frames on the upper part. Also, this one is a little bit special because here we have the attachment point for the THS actuator. Yes, and as you can see, it's really special here. It's really special because it has to take the loads of the THS. The rear pressure bulkhead consists of 11 aluminum alloy segments, and it's making this aft or rear pressure bulkhead. We have a dome and a ring, which is closing actually the pressurized fuselage. On these segments, we have openings in which we install the positive and the negative relief valves. Remember, the safety valves. They are directly riveted to the doublers. And once again, you see doublers because everywhere with these openings, we have reinforcement. We have to increase the strength of the structure. That's why we have doublers here. Okay. Also, we have for the APU bleed line, also we have some openings for communication of hydraulic system and wiring. All these doublers and support fittings are internally made of aluminum alloy. Have a look. 11 plates making this dome, this circle. Have a look. Negative, positive pressure valves location. And have a look how many small like a holes we have. So there are some, as I said, hydraulic lines or electrical wiring, but not only electrical, but also different harnesses, which are also fuel we have, which is for the APU. And we have some specifics in these openings. We have specific pressure seals, which are keeping, of course, this cabin pressurized. So this is the ring and the joint splice here. Joint splices between the different plates here. Okay. Floor supporting structure, as I said, the difference is that between 90 and 90 alpha, we still have this pressurized fuselage. This is the floor structure for the aft avionics compartment. If you remember, I told you aft avionics compartment is located just behind the aft lavatory and aft galley. And then between 90 alpha, which is our pressure bulkhead, until frame number 100, we have this unpressurized area and our THS compartment. So here the specific floor structure looks like this. We have C and L cross-section beams, which are like secondary support, secondary structure. They're not taking any pressure loads. They're just keeping the loads from our weight, as I said, for maintenance. And also we have one cutout, which is our service door to access the THS compartment. Inside, you can find, you remember what is located here, forward from the door. We have hydraulic system 3 components. Okay, here behind we have our THS actuator, and which is attached on the top to one of these special frames. This one, the special machined frames. Okay, intercostals. These components here are called intercostals, and they are, how to say, they are similar. They're replacing the function of the stringers. But once again, the name of the component is not a stringer, but it's called intercostal. As you can see, they are providing this connection between the different frame segments, and they're keeping the structure here of this unpressurized part of the rear fuselage. Have a look. They have specific shape, and they are not like stringers once again, but the function is similar like the stringers. But because of the different design and the different shape, they have different name, intercostals. From frame here 93 to 96, 97, 100. Okay. Vertical stabilizer to rear fuselage attachment. The vertical stabilizer front spar attached to frame 92, middle spar is at 94, and the rear spar is at frame 97. Later, tomorrow, we are going to talk about the vertical stabilizer, and we are going to mention again these attachment points, but it will be from the point of view of the vertical stabilizer. Now, because we are talking about fuselage, these are the frames which we have these attachments. This crown area of the rear fuselage, which is again non-pressurized of course, has 8 tension bolts on each vertical stabilizer spar, and we have totally of 24. Because we have 3 spars, on each place we have 8 bolts. This is how it looks like from the top. Looking from the top, these are the frames. Here, here, and here. In each location we have 8 bolts. Special bolts, and this is how the vertical stabilizer is attached to the structure. And you understand what kind of aerodynamic loads we have on the vertical stabilizer, and that's why the structure here is really, I would say, really with increased strength to keep all this weight and all these aerodynamic loads. Each of the vertical stabilizer spar root is in direct contact with 2 joint fittings here. And as I said, 8 bolts here, 8 bolts here, 8 bolts here. It will be much more easier when you talk about the vertical stabilizer, then we're going to talk about these attachment points. When you talk about the horizontal stabilizer, we have fail-safe aluminum alloy hinge fitting assemblies in the rear fuselage, which are directly riveted to this rear fail-safe fitting, close to frame 100. We have 2 tie rods on the top, which are connecting with the intercostals, and we have adjustable tie rod, which connects both sides of this hinge here. Just a second. Have a look. So this is the horizontal stabilizer, and we have these attachments here. We have rods which are keeping together the structure. This is how it is attached with closer look here. Again, with bolts and nuts. And again, we have a really strong structure because there are a lot of and high aerodynamic loads coming from the elevator and the horizontal stabilizer, like in general. When you talk about the tail cone, again unpressurized section, and we have the APU there. The APU is located here in this tail cone section. There's something specific because this tail cone section has 4 bolts and can be removed. It is written that in some cases you can remove the tail cone section. Of course, you have to remove also the APU. Yes, you have to remove the APU. I don't know for what reason you can do that, but anyway, it's written that we have these 4 bolts, and you can remove the entire section. It's attached to the rear fuselage by means of 4 bolts in the firewall region, and it's fully removable from the aircraft by removing these 4 bolts. It's made from forged aluminum alloy, and we have access panels which are made by aluminum alloy and steel. We have openings for the APU inlet, we have opening for the APU exhaust, we have some openings for the drains, And you know that the APU is a line replaceable unit. You can just remove the APU if it's necessary to replace it or for some inspections. We have the forward section of this tail cone with firewall fixed and movable portions. You know that the APU is a fireproof compartment. In case of fire in the APU, yes, we have detection system for fire, but also it is fireproofed, and this is to prevent spreading of this heat, the fire, to the structural components. The APU is attached with 7 struts to the rear fuselage. We have 3 mounting points on the APU, but we have totally of 7 struts, which are attaching to the structure once again. In details, when we talk about the APU, actually with my colleagues, when we talk about the APU. We have this silencer. The tail cone, the aft side of the tail cone has silencer. By the way, the silencers is very effective, and the APU is not noisy. If you compare with other APUs, this APU is not so noisy. By the way, I'm really happy of this APU. It's very reliable, with extremely low oil consumption. It's a FADEC type, but this is something related with the APU design. My point was that this silencer, which is on the rear, this tail cone, it's something very good, like engineering design. And the exhaust system, the skin of the exhaust system is made from Inconel. Inconel and aft portions are made from aluminum alloy. This Inconel is resistant to high temperatures. Okay. Here it is, the silencer and the APU. At the bottom, we have the access panel, the cutout for the APU, and we have also some openings here for draining, for the drain mast, and we have here on the upper right corner, we have inlet for the APU air inlet. And here we have example for the allowable damage on the skin. We already talked about the standard practices. We talk about the fuselage chapter 53. You are, I think, already familiar with evaluating evaluating damage. And have a look. Why I'm saying all the time that the structural repair manual of this aircraft is very friendly. It's very friendly because if you have damage somewhere, for example, dent here, you can open the SRM. Okay, first of all, you have to identify the location. Do you remember the steps, the logic? First, you have to find the exact location. So if the damage is here, it's between frame 8. Sorry, I will zoom a little bit. So it's between, where was the damage? Here, okay. Between frame 9 and frame 8. And it's between stringer 12 left and stringer 13 left. So we know the exact location, yes? Also in this SRM, structural repair manual, you have these different colors, different shading of the skin panels. So if you have a dent here, you see that we have this A panel, and you can check what is the skin thickness. So here, the skin thickness is 0.8 millimeters. Can you imagine?
Yeah.
The same thickness you have on the jars, on the cups, on the glass jars. Okay, so very easy. We identify now where is the damage and what is the skin thickness. So if you have a scratch, we said this scratch we have to blend out. When we blend out, we remove part of this skin thickness. So we have restrictions. This is what happened in my case with these structure guys to start to blend out, but it was not on the left side, it was on the right side, I think, anyway. So he started to blend out, and then suddenly, when the NDT guy measured the remaining thickness, it was out of the limit. Okay, that's why I told you, be careful when you're performing blend out. Okay, on some locations, the skin thickness is really low. Fuselage stringer repairs. This section will deal with the typical stringer repairs for all stringers applicable to the fuselage. And you always have to keep in mind these specifics when you do repairs, which are including these RVSM warnings. You know what is RVSM? This is the separation between the airplanes, you know, the zones which are near to the air data props always have to be smooth and clean to provide proper air data inputs, and also this will increase the reliability of the air data system, which will keep the aircraft flying on specific flight level. So in this case, the airplanes, they can fly in a reduced separation. But this is something else. And something really typical for Embraer, most of the times when I have damage which is not listed, I have to contact Embraer. There are a lot of restrictions in the allowable damage tables, and once again, if your damage is not allowable and also you have no idea how to proceed, you have to contact Embraer. But keep in mind that when you contact Embraer, you have to pay. This service, this assisting service for Embraer is expensive. Have a look here, the stringers are shown, the frames, and if you remember, in the forward fuselage section, we have different number of stringers, and as forward we go, the number of the stringers is reduced. Okay, just to remind you, because it's the same chapter now. Stringer repair, we have these shims to repair the string. Damaged part of the stringer repair, you can see here. To be honest, I'm not so familiar with this type of repairs because I never study about this, but this is just an example how it looks like. How it looks like to replace part of the stringer. Fuselage frame repairs, again, if your damage is not in the limits, and I told you at the beginning of this chapter, damage on the frames, damage on the stringers are usually not acceptable. Most of the times they are related, let's say almost all the times they're related with some replacement or at least some repair. That's why you have to be really, how to say, you're really careful. And because you understand that the structural repair manual cannot give you a standard repair for all the frames, because you already know from the information that we pass through, you already know that on the different locations we have different frames, yes, different shape, different type of frames, machined frames, C-shape frames, U-form frames, and it's not possible for the manufacturer, for Embraer, give you a general repair for individual damages. That's why most of the times when we have this kind of damage on stringer or frame, we have to contact Embraer. Their engineering team will make calculations and we will advise you for the proper repair. When the structure guys, the professionals, they have the instructions for the repair. It's not a problem. They just need the spare parts, the rivets or clips or whatever they need, and they can perform the repair and to certify. But as I said, we have such a big number of differences in the structure depending of the section, depending of the specific location. So in many cases, it's not possible to have like a general repair. It's not possible then Embraer to say, all frames you're going to repair with this procedure. All stringers you're going to repair with this procedure. No, because we have different locations with different structural specifics. Okay? And one more time, because I already said, but one more time. Maybe you have the same zone, the same type of damage, but because of the different size of the damage, you can experience different repair. Okay? Passenger seat tracks. Here, different repairs we have. Again, very important component, the seat track, which is keeping the seats and the passenger weight. We have some restrictions. Usually these seat tracks, they experience some corrosion and some cracks. Corrosion is very easy to grow up here because, you know, when we install the seats, we're using a very short distance and the rest of the seat track is just open. And these seat tracks are always full with some garbage, some dirt, and this dirt is absorbing moisture. And this moisture is all the time staying here and sooner or later is making corrosion to the seat track. Also, as a standard practice, because when we talk about the cabin floor structure and the seat tracks and the floor panels are installed with sealant. I mean, yes, we have screws to mount to install the panel on the floor structure, but then the gap between the floor panel and the seat track we have to fill with sealant. And according to the standard practices, we have to use plastic scrapers, plastic or wooden scraper to remove the sealant so we can remove the panel, okay? It's not enough if we only remove the screws. We also have to remove the sealant. But some guys, they know that if they use metal sharp objects, they can much easier and much faster remove the sealant. You know about this, yes? You're experienced. But when you use metal scrapers or these metal sharp objects to remove the sealant, it's very, very easy by mistake to scratch the seat track surface or these beams. And then we have a problem. Because when you scratch, okay, the aircraft will not crash because of the scratch, but because of the scratch, you disturb the paint, also the primer layer. So now the seat track structure is exposed to the moisture in the cabin. And as I told you, sooner or later, there will be corrosion. So it's not something so dangerous if you scratch the structure of the seat tracks. Just clean and protect. Protect with primer, protect with paint, everything is fine. Okay, just protect. I'm talking about small scratches, of course, but again, please follow the instructions and use plastic scrapers or at least not metal scrapers, not sharp objects. One of my colleagues, old guy, very funny, he's saying, Živo, I love my non-metallic titanium scraper. Okay, it's again non-metallic because in the maintenance manual is said to use a non-metallic scraper, but his non-metallic is made from titanium. Okay, it was kind of joke, of course, because the titanium is very sharp. Yes, not sharp, but very strong metal material. So guys, that was the fuselage chapter here. Well, I know that we passed through many different structural components, maybe a big number of new terms that we use, but don't worry, it's not so scary. I think that you have the general idea about the different sections, the specifics in each section. And you're smart guys, I'm sure that you're not going to have problems with this, okay? So, nacelles and pylons. The aircraft pylons support the left and the right engine. The purpose is to transfer the engine loads to the wing structure, and the wing structure will transfer the loads to the fuselage structure. The pylons are symmetrical structure in the fuselage, and as I said, they are supporting the engines, transmitting the loads using the mounting system. We have mounts, which are transferring once again the different engine loads to the wing, and then the wing to the fuselage structure. So what we have? We have upper links, lower links, and aft links. The upper links are connected to wing spar number 1. The lower links are connected to the wing lower skin here, and the aft links, they are playing like a drag strut. They are attached to wing rib 8 alpha. Now we're looking from the pylon point of view, and when we talk about the wings, again, we will mention the structural components, these attachment points, but looking from the wing point of view. So once again, the wing upper fittings to the front spar number 1, but on ribs 8 and 9. You understand that along the wing we have ribs, yes, ribs like this. Okay, and this element is called spar. So the upper link fittings are connected to the wing ribs 8 and 9. The lower fittings are connected to the skin, but at ribs 8 and 9. Okay, the same ribs, just one is on the front spar, another are on the lower skin. And this drag is the rib 8 alpha. The pilot box structure is holding the loads and the moments transmitted by the engine, the nacelle, the thrust reverser in all 3 axes. And to improve the aerodynamic, we have these fairings. We have movable and aft fairing. We have this main structure, which is used like as part of the pylon, and we have forward and lateral fairings. They are composite. They're composite materials. What else? What else I can tell you interesting? We have 12 frames. The main box has 12 frames from number 1 to number 12. And also, when you talk here about this attachment, these attachments to the wings, now here we're talking about the rims and the spars which are on the wings, okay? These numbers here are from the wing structure. Ribs 8 and 9 here, ribs 8 alpha, they are part of the wing structure. And here we're going to talk now about the pylon frames. We're going to talk about the pylon box and the pylon structure. The materials which are used in the pylons are usually stainless steel or titanium alloy. The lower part is machined from stainless steel because of the possible leaks of skydrow. Because inside the pylon we have these hydraulic communications, fuel, electrical harnesses. So stainless steel is more resistible to skydrow. The upper part of the box is made from aluminum alloy. This is to meet the bird strike requirements, to be resistant of impacts with birds. So now we have some differences in the different frames. Frames 2 and 3 are machined from stainless steel because of the skydrow, as I said, and then from 4 to 12 we have titanium alloy. Frames 1 and 3. Okay, let me show you here. Why I'm not showing you this schematic here. Okay, different frames. As I said, from frame number 1 to frame number 4, we have aluminum alloy. The rest are titanium alloy. And engine is attached to two mounts. One mount is in position between frames 8 and 9. I'm sorry guys that I'm changing here this blocking. This forward mount, here is the aft mount between frame 4 and 5 and between 8 and 9. So the loads from the engine in the pylon box is transmitting these loads to the wing. If you pay attention here on these attachments, okay, then we can compare with this coding the side, the vertical loads, together with torque and the pitching moment. The aft mount is holding also the engine thrust. Okay, all these mounts, all these loads like the side, vertical, and torque. Okay, just let me compare side, vertical, torque, pitching moment. They're common loads which are transferred by both mounts. But the aft one has also the thrust and the yaw. Keep that in mind. They are transmitting different loads. Most of them they're same. The side loads, the vertical, which is actually the load of the engine, the torque, because of the rotation of the components like fan, like turbine, compressor. So this side vertical and torque loads are from both mounts, but we have thrust loads, engine thrust, and the yaw moments, which are transferred through the aft mount. So we have to remember these different mounts and the loads that are transferred. It is important here for the operation and the structure of the components. This is how it looks like, the attachment on the lower wings. This is our thrust link. Okay. Of course, the fairing is removed. The fairing is removed, and you can see here hydraulic lines, fuel lines passing through. And that's why here in the forward zone we have stainless steel, not stainless steel, but aluminum and steel frames. Stainless steel, okay, not aluminum, my mistake, stainless steel, my mistake. The fairings, they are providing this aerodynamic smoothness. So the airflow which is passing around the pylon will go also smoothly to the wing. And the fairings that we have are forward fairings here. We have lateral fairings on the side. We have also heat shield, because here where the heat shield is, this is where our pneumatic ducts are passing for the engine bleed. Here on the aft, we have movable fairing. Actually, on this schematic, here the movable fairing is missing. It's removed. These fairings are composite material. And that's it. So Pi1 is attached to the wing, on wing ribs 8 and 9. On the upper link, lower link is on the lower area, on the lower skin, ribs 8 and 9. And this aft lower and this single fitting is to the rib 8 alpha. We have 12 frames on the box. We have 2 mounts. The forward mount is between frames 4 and 5, and the aft mount is between 8 and 9. And we have different loads which are taken between the different attachments here, different mounts. And the difference is that the aft mount is taking additional loads like the torque and like the yaw moment. The rest of the loads are the same. We have 3 hinges on each side of the Pi1 between frames 1 and 4, which are attaching this engine intake nacelle. We have separate hinges on each side of the Pi1 between 5 and 6, which are for the thrust reverser cowling. Because the Pi1 is also a structural element which is keeping the loads from the fan coils here and the thrust reverser coils when they are open for maintenance. And that's it. Any questions? Okay. No questions. We're going to talk about horizontal stabilizer, vertical stabilizer, elevator, and rudder. So the stabilizers are attached to non-pressurized section of the rear fuselage. We talk about this, and this stabilizer have aerodynamic controls. We have elevator for horizontal stabilizer, and we have the rudder for the vertical stabilizer. And this horizontal stabilizer, you know very well, we also call it trimmable horizontal stabilizer, and you know how it works already. And both elevators are hinged to the horizontal stabilizer. The stabilizer is all metal, 3-spar construction hinge to the rear fuselage. It is a movable control surface. We have 2 sections, left and right section, which is coming together inside the THS compartment in the central line, but they can be removed as a single unit. Just in a while, we're going to see that we have splices which are making this left and right parts of the horizontal stabilizer together. About the elevator, you know, non-balanced flight control surface. We have 5 hinge fittings. We have 2 PCUs, which are controlled by LVDTs, correct? You still remember the flight controls, yes? Each elevator has 2 PCUs. Vertical stabilizer, similar to the horizontal one, all metal surface, again with 3 spars, construction, which is cantilever, which is a fully cantilever sweep back structure attached to the rear fuselage. And we have 24 bolts, yes? We have 3 locations with 8 bolts on each location. The front and the rear spars, they extend alongside to the full length of the vertical stabilizer. And the rudder is a balanced flight control surface hinged to the vertical stabilizer by means of 5 hinges. Okay? There were 5 also for the elevator, 5 also for the rudder. Again, the rudder is actuated by 2 PCUs, and control is coming from LVDTs. Pedals transmitting this mechanical input to electrical signal. You remember PAs, flight control modules, electrohydraulic servo valve in the PCU, and then we have this operation of the rudder. So vertical stabilizer is stationary, but the horizontal stabilizer is movable. Okay. Now, a few words about the horizontal stabilizer. So the horizontal stabilizer surface has this, once again, all metal structure, and both halves, both parts, the left and the right side, they're coming here in the center line, and they're coming together because of this here. Actually, it's on this next picture. Just a second. These upper and lower splice plates. Upper and lower splice plates. This is how both parts are coming together. But now in the previous picture, we can see the structure. And do you remember, we have these openings of the rear fuselage because the forward and the aft area of the actually the entire horizontal stabilizer is moving. And because it's moving, we need enough space, opening which is big enough to provide this movement of the horizontal stabilizer. But we don't want the airflow to go inside the compartment. We have to protect it. And for that reason, we have some fairings and sliding plates. Here on the leading edge, we have a sliding plate, you see? Sorry, sliding fairing. Sliding fairing, which is making aerodynamic transition between the rear fuselage and the leading edge, okay? This is an aerodynamic component to improve the smoothness, and it's called sliding fairing. But above and below the horizontal stabilizer, we can expect some gaps to appear, and these gaps are covered by sliding plates, upper and lower sliding plates, because when the horizontal stabilizer is moving up and down, these plates are moving together, and all the time the gap, the hole, let's say, on the fuselage is covered by the plates. They are sliding inside on the inner side of the fuselage. So once again, when the stabilizer is controlled the leading edge up or down direction, the sliding fairing is sliding to provide this aerodynamic here in the front, but the sliding plates are keeping the airflow not to go inside our THS compartment. The structure has three spars, as we said, all metallic. We have the front spar, we have the rear spar, and we have the middle spar. And we have 17 ribs. Ribs. All this metallic structure is covered by upper and lower skin panels. These upper and lower skin panels are protecting, the structure, and they provide this smoothness, of course, like the wing to be flat and smooth, as I said. We have these splices which are coming together, as I said, to make both halves like one assembly. We have upper plate, lower plate, and in addition, we have these vertical splices here and here. So they are creating this one unit, the vertical stabilizer to be like one unit. What else I can tell you interesting? Well, here we have description from which rib to which rib is extending the different spars. No need to remember this. Please remember that we have front, middle, and rear spars. And the important on the rear spar is that we have attachment for the elevator. 5 hinges for elevator attachment. On the front spar, we have the leading edge attached. Elevator. Five hinges, we said. The elevator is all composite structure. Okay, all composite structure. And what else I can tell you? This is how it looks like when both parts are assembled together with the splices. And this is how, with these hinge fittings, I'm sorry, because okay, these are the hinge fittings where we attach. Tell me what.
The jet actuator.
Yes, the trim actuator. The trim actuator we attach here in the forward area. On the aft, we have these hinge fittings which are attaching the aft part of the THS. And it was written that it can be removed as one assembly. I never seen that, but this is what they say in the manual. So this is how the horizontal stabilizer is attached. On the rear with these two hinge fittings, and in the front to the trimmable actuator. So now you know when we have this actuator, the ball screw, sorry, yes, the ball screw is like here. When it turns, it moves up and down this forward edge, this leading edge of the trimmable horizontal stabilizer, and this is making nose up or nose down inputs. About the elevator, you know how it works, like a flight control. The important here for the structure is that is all composite. All composite made up of two spars, ribs, skin panels, and trailing edge assembly with removable root and tip fairings. We have root fairing and tip fairing, but it's all composite. And again, we have the standard structure inside the composite, which is for this important flight control, these ribs and spars. So this is how it looks like looking from the top. 5 hinges are the attachments of the elevator for the rear spar of the horizontal stabilizer. We have some specific locations for the actuators to install the actuators, and we have, as I said, these fairings here, which are for the improve the aerodynamic. The deflection range is nose up 25 degrees, nose down 18. Vertical stabilizer. Vertical stabilizer, similar construction as the horizontal one. All metallic structure, 3 spars, the front spar, the mid spar, the rear spar, and we have ribs. Okay. Again, on the rear spar, we have attachment for the rudder, which is again with 5 hinge points. And on the front spar, we have the leading edge. The leading edge. And something specific here, on the lower area here, we have component which is called dorsal fin. This dorsal fin is similar to our sliding fairing. Okay, it's similar to our sliding fairing, and the purpose is to improve the aerodynamic smoothness between the fuselage and the vertical stabilizer. It's making the airflow to pass smooth here. Also, here in this area, which are related with the HF antenna, with the high frequency communication system. But the antenna is here, the leading edge. What else? The rudder, all composite, 5 hinges. We have this structural box here on the bottom. Why? To attach to the rear fuselage. These bolted joints. Do you remember the bolted joints here? In 3 locations, 8 bolts in each location. Yes? And this is another point of view for the rudder access panels. We have some access panels to access the hinges for inspection or lubrication. And also we have access panels to access the PCUs, the rudder PCUs. In addition, in the vertical stabilizer, we have additional access panels to access the vertical stabilizer structure. I didn't told you, and it was also not shown here, but we also have access panels for the elevator PCUs. But we have no access panels for the structure here on the horizontal stabilizer, only to the vertical one. And when you talk about the rudder, again, composite structure. Again, we have spars, we have ribs, 3 spars, ribs, skin panels, trailing catch assembly with removable root and tip fairings. Same like the elevator, like philosophy, like components, like structure, like, of course, they're not the same, but looking from the structural point of view, they're the same. All composite with the same structural elements, 3 spars, ribs, skin panels, trailing catch, removable root, and tip fairings. Same. Again, we have LVDTs. Again, we have 2 PCUs to control the elevator surface. You know about this. And in the structure, we have copper mesh plies, which ensure the electrical conductivity. Once again, because on these structures, we have a lot of airflow circulating around, it is possible to have static charge accumulated. So this copper mesh will transmit this static charge to the rest of the aircraft structure. So these are the hinge fittings here, root fairings, tip fairing. By the way, during one lightning strike, we found this tip fairing was missing, not damaged, just missing. Maybe the lightning hit the fairing. I don't know what happened exactly, but we were waiting long time for delivery of this tip fairing. During this time, we dispatched the aircraft according CDL, configuration deviation list, something that we're going to practice also during the practical training. So the leading edge here, the mid spar, and here we have the trailing edge. Sorry. This is the rudder, my mistake. This is the rudder, the structure of the rudder. We have the leading edge, trailing edge, and the rear, and the spars here, okay? And we have skin. On the left and the right side, we have skin to protect the structure. And we have access panels, as we said. What else? That's it. So tell me, do you think it's difficult here? Any questions?
Question, please.
Yes, tell me.
So when you park your aircraft at night in snowing weather, do you have a tire tail support to protect?